I want to show you what happens with just one little change to our input data for the logistic regression. Here's what we had before. Everything was kind of centered on x equals 10, but with this code, I'm going to standardize the x values. That makes their mean equal to 0 and their standard deviation equal to 1. So I have some code in here that says you want to standardize or not. If you do, then it standardizes the data here. For the x values, when we're doing logistic regression, we don't standardize the y values. Those have to stay at 0 and 1. If we were doing plain old linear regression, then we do often want to standardize the y values. But here's the plot we get. Notice that 0 is now in the center, and it doesn't go out to like -5 and +5. So let's see what effect this has on the optimization. We'll come down here. And are you getting dizzy yet? We'll find the contour plot. Okay, so here's the surface plot. So that does not look as squished as it did before, right? Before it looked like one long trough, kind of. Here's a heat map that's looking not as long and trough-like. It's kind of interesting that the x-axis and y-axis are -2 to 2, -2 to 2, but we don't see perfect symmetry. It's a little higher here than it is there. And look at our contours now. They're much more like circles than ellipses. We can see they're not perfect circles and they're not perfect ellipses. But what effect did this have on Newton's method versus steepest descent? Now they look pretty competitive. Let's see, hard to see any difference there. Just the major iterations, hard to see any difference there. Our animation actually won't show us very much, so we'll skip the animation. And in this history of the objective function values, as we look at how many steps, minor iterations, steepest descent actually looks better than Newton's method. And that's what we see here too. This is the magic of the semilog y scales, right? It kind of lets us see all that. It looks like steepest descent actually found a solution better than Newton's method, and it found it faster. So that's the magic of adjusting your problem so the contours are more like circles than really squished ellipses. In some sense, what we're doing is called preconditioning. Problem with really squished ellipses is said to have a bad condition number, and we'll talk more about that later. It relates to eigenvalues. But preconditioning makes the condition number closer to 1 and makes those closer to circles. And then steepest descent is actually kind of faster than Newton's method, because what Newton's method is doing is conditioning, not preconditioning, but doing conditioning at each step. But if we precondition once in a really good way, then we don't need to condition at each step, and steepest descent can actually kind of win. So it's really important to think about how squished your contours are, and whether all your numbers are in kind of the same rough sizes. Like, you don't want some numbers in nanometers and other numbers in kilometers. You want to keep everything in the same ballpark range, and that helps keep your contours circular or spherical roughly, rather than really squished ellipses and ellipsoids.